Hello. So the next question is, why finding the period so important to leverage the power of quantum computing? So let's hear the answer.
Okay, finding the period of a function is critically important because it's the core quantum subroutine that unlocks the power of quantum computing for solving certain problems exponentially faster than classical computers. The most famous example is Shor's algorithm for factoring large integers. Here's why period finding is so crucial. 1. It reduces hard problems to something quantum computers excel at. Many computationally hard problems, most notably factoring the large numbers used in RSA encryption, can be mathematically reduced to the problem of finding the period of a specific periodic function, usually involving modular exponentiation like f of x equals a caret xp mod n. Classically, finding this period r for the function f of x equals a caret xp mod n is believed to be as hard as factoring n. There's no known efficient classical algorithm for it when n is large. 2. Quantum Fourier transform, QFT, is efficient. Quantum computers can perform the quantum Fourier transform QFT very efficiently. The QFT is the quantum analog of the classical discrete Fourier transform, DFT. The QFT has the remarkable property of being able to efficiently reveal periodicities hidden within a quantum state. How it works, conceptually. A quantum computer uses superposition to prepare a state that encodes values of the function f of x for many different inputs x simultaneously. Applying the QFT to this state transforms it. The properties of Fourier transforms mean that if the original state encoded a periodic function, the transformed state will have high probability amplitudes concentrated at points corresponding to multiples of the frequency, which is related to the inverse of the period. Measuring the output state after the QFT gives information, with high probability, that allows classical post-processing to determine the period r. 3. Unlocking exponential speedup. While a classical computer might have to evaluate f of x many times to find the pattern, period, a quantum computer uses superposition to evaluate it effectively for many values at once, and then uses the QFT as a highly efficient lens to extract the periodicity. This ability to find the period r efficiently, in polynomial time with respect to the number of digits in n, is what gives Shor's algorithm its exponential speedup over the best-known classical factoring algorithms, which run in sub-exponential but not polynomial time. 4. Broader applicability, hidden subgroup problem. Period finding is a specific instance of a more general class of problems called the abelian hidden subgroup problem, HSP. Quantum computers are known to be efficient at solving the HSP for abelian groups. Besides factoring, solving the HSP has implications for other problems, including some related to cryptography, like breaking discrete logarithm-based systems, and potentially other scientific domains. In essence, finding the period of certain functions is the quantum magic trick enabled by the QFT, operating on states prepared using superposition. Because several extremely important and classically hard problems, like factoring, can be boiled down to needing this period, the ability of quantum computers to find it efficiently is a primary demonstration of their potential power and the reason they pose a threat to current cryptographic standards like RSA. It's the key that unlocks the quantum advantage for these specific but significant computational tasks.
Alright, there we have it. So the key things, hard problems to something quantum computers excel at. So when we have these periods, finding the superpositions and how the interference works, constructive interference and destructive interference, it leads to easily finding the period. It makes QFT efficient and it's unlocked this exponential speedup, and also it has this broader applicability to other problems like hidden subgroup problems. So quantum computers are known to be efficient at this solving the HSP for abelian groups. Besides factoring, solving the HSP has implication for other sub problems, including some related to cryptography, of course. So yeah, there we have it.